For an early hominid, eating was a grueling full-time job. Without a way to cook, surviving on a diet of raw meat and tough roots meant spending up to 6 hours every single day doing nothing but aggressively chewing. That relentless daily grind came with a steep anatomical cost. Processing raw, fibrous food required massive, heavy jaw muscles that anchored deep into the skull, which physically restricted the space available for brain development. Out of more than 8 million species on Earth, human beings are the only ones that cook their food. Cooking acts as a form of external predigestion. When you apply high heat to raw ingredients, it breaks down the tough proteins and fibers before they even enter your body. By using fire to extract 10 times as many calories in a fraction of the time, our ancestors initiated a biological trade-off. As massive jaw muscles shrank, the skull cavity expanded, and the brain inherited the energy once required for digestion. But this shift created a precarious new reality. Our newly expanded, highly complex brains now burned massive amounts of energy. We absolutely depended on high-calorie cooked food just to survive. Early humans could no longer passively wait around for a random lightning strike or a natural wildfire to provide a flame. They needed it on demand. Solving the strict engineering problem of creating fire from scratch became humanity's most critical survival imperative. Humanity's version 1.0 solution utilized raw mechanical energy and friction in the wilderness, the hand drill. The physical setup is incredibly simple. You take a vertical wooden spindle, place it into a notch carved on a flat wooden fireboard, and roll it rapidly between your palms while pressing downward. It is a pure application of thermal physics. That rapid spinning motion concentrates friction into a tiny surface area, generating localized temperatures that push 800 degrees Fahrenheit. At the microscopic level, the friction physically wears the wood fibers away, crumbling and grinding them down into a fine, superheated black powder. The intense heat ignites this charcoal dust into a single, glowing coal. You gently tap that coal into a bundle of dry tinder, blow oxygen directly onto it, and catch a flame. Mastering this mechanical friction pipeline freed early humans from a total reliance on natural forces. They now had a portable survival tool that allowed them to migrate across the globe. By the time of the Iron Age, humans needed a faster, more reliable, and far less labor-intensive method. They engineered the tinderbox. This replaced wooden friction with kinetic percussion. The technique involves violently striking a hard steel tool against the incredibly sharp edge of a flint rock. In this microscopic kinetic reaction, the rigidly hard flint edge physically shaves off microscopic pieces of iron from the steel striker. Intense friction rapidly heats these sheared shavings to their ignition point, causing them to instantly oxidize, burning in ambient air, and create hot sparks. Replacing the exhausting friction of the hand drill with kinetic impact and rapid oxidation created a highly efficient portable ignition tool that rapidly accelerated human technological progress. Today, the modern pocket lighter acts as version 3.0 of human ignition, a device that synchronizes percussion and chemistry in a fraction of a second. The modern iteration of percussion relies on a spinning metal wheel scraping against a synthetic alloy called ferrocerium. This material is engineered specifically to throw a massive shower of sparks, burning at over 3,000 degrees Fahrenheit. Simultaneously, a mechanical delivery happens inside. As your thumb rolls the wheel, it presses down a tiny plastic fork lever. That lever lifts a microscopic valve, releasing pressurized butane gas exactly as the sparks fall into its path. The result is instantaneous combustion. The steady flame contained within this pocket-sized pressurized valve produces the exact same energy that shrank our ancestors' jaws and expanded the human brain case millions of years ago. From rolling sticks in the dirt to syncing precise kinetic impacts and microscopic chemical reactions, our ability to command fire remains the prerequisite for everything else we have built.